I wish to quote here, Israel more ayur. Every great building once began as a building plan. It is same with the dreams. Mr. Bob von Gils also dreamt of having their own design office in India and overseas, and he realized it. Mr. Bob von Gils was educated as a structural engineer in the Netherlands, where he completed his bachelor degree with a specialization in structural engineering. He started his career in Netherlands in 2001 as a structural engineer with structural design firm Van Boxel Engineering, where he mainly worked on design of reinforced concrete and precast concrete building structures. He was part of the team that completed the precast detailed design of the Daimler Chrysler office building in Utrecht, which won the prestigious award for best concrete structure of the Netherlands in the year 2003. Mr. Bob von Gils relocated to Gurgaon, India in the year 2005 to establish the India office of Van Boxel Engineering Private Limited, which is a direct subsidiary of the parent company in the Netherlands. In 2010, he co-founded the present design company WBK Engineering Services Private Limited, and nowadays Mr. Bob is in charge of the WBK India office. Mr. Bob is vastly experienced in reinforced concrete and steel design and also precast concrete design, and he has worked on a large number of building projects throughout his career. He is also a regular speaker at conferences, published author, licensed structural engineer, and chartered engineer of the Institution of Engineers India. WBK Engineering Services Private Limited under Mr. Bob has established an experienced precast design and detailing team in their Gurgaon office. They are involved in design and detailing of same state-of-the-art precast building projects in Europe, USA, and India. Now I request Mr. Bob to come over to the dais.
Good afternoon, all. Everybody's here. My name is Bob. I'm here to present about some case studies of precast residential buildings in India on which we have worked. I would like to thank the PEPSCON organization for inviting me for this event. And let's start with the presentation. Oh, that side. I'd rather stand here, maybe better. So this presentation will be 3 projects in India. One is a group housing project in Ghaziabad. The second one is a group housing project in Bangalore. And the third one is precast villas in Greater Noida. We start with project 1. This project, these are all a little bit approximate figures. Area is around 60 acres. And there are approximately 5,000 apartments with different sizes of houses. And the total project was a basement plus ground plus 14 floors. And this was a private real estate developer who had the idea of, instead of doing his project in cast in situ construction, to utilize new technology and start with precast concrete. There's an idea about the master plan, approximately this area. This area is precast concrete structure. The phase 1 which they did was initially, where the project started, was cast in situ. There's an idea about the towers. So these are basement plus ground plus 14 blocks of, you could say, 1 BHK, 2 BHK, and 3 BHK flats. So I will explain a little bit about the building system, the design aspects, the details, the execution of this project, as well as some of the manufacturing aspects. So the system was as such that basement and foundation was cast in situ, and everything above that is made as precast concrete. And that means mainly in these kind of building projects of apartments are wall panels and slabs. As we had seen also in some of the presentations in the morning, If you already have these houses, you have all these walls, you're utilizing that as a load-bearing structure of wall panels, just make it very convenient to quickly construct. And it was also, as such, as all these walls can be acting as structural walls. It's a shear wall system which can, when you detail it properly and tie it properly, can very well behave as an earthquake-resistant structure. So a very simple concept. I mean, we have walls. Then we have the floor slabs, and we have a reinforced concrete topping, and then you keep on going on. Stand a little bit closer. Doesn't work. So panels are floor-to-floor height, generally, in precast. That has to do with the manufacturing aspects. The elements in this project. Hello. Elements in this project, load-bearing walls of 200 mm and 160 mm thick, partition walls, shaft walls. We had slab system in this project, which was half slab system. I will show you that in detail. Then we had, so this will give you a little bit of overview of the elements that were there in this project. So we have precast solid wall panels, L-shaped walls for the shafts, the partition walls, which are just 100 mm non-load bearing, the precast half slab. So this system is a system where you have half precast and the other part is cast in situ concrete. And you have these lattice girder reinforcement coming out and the roughening of the top surface, which basically creates a bonding between that precast and cast in situ. So how does that work? You have your walls. It's just a general idea. You place a propping system. Then you have your half slab, which is having the bottom reinforcement inside the slab. You have the lattice girder reinforcement coming out. Then you place additional reinforcements at site for tying this. And then your top mesh, as well as all your tie reinforcement. And then you place shuttering, maybe required a little bit at the edges, and you cast your topping. Remove your props, and then you have a sort of a monolithic structure. What more we had in this project were all the exterior balconies were fully solid precast panels with actually protruding reinforcement at the end to connect with that topping. We had precast stairs, landings. Yeah, are we? Not going anymore. Beams. Right. So some of the aspects of execution and the detailing of this project. So as I said, the raft foundation as well as the basement structure. As the basement structure had a different height, we discussed with the client that it would be easier in this case to make that entirely as cast in situ. So that looked like this. This is like what most of the people know from conventional construction. What we did is almost, I think 80 or 90% of the shear walls of the superstructure are actually going down all the way to the foundation. So that means that underneath your towers, you'll have a little bit of limitation in your parking, and the parking has to happen more outside of the tower area. So as this was reasonably high seismic zone, it's at Ghaziabad, the seismic zone 4 in India, these kind of revisions are very important. So how does it look? You have, this is the basement structure here, and then on top of that you have your precast structure, load-bearing wall panels, as they are assembling here, slabs, and the entire balconies and everything. So what is the process? You place your walls, you place your bracings, temporary bracings. A lot of people might know this, for some people it might be new, so just give a little bit of an idea of what is happening there. So your ground floor will be walls, then you place a propping system for these half slabs, because these are, you have to support them temporarily. Then you place all these slabs. So all of this will be placed by crane, of course. Then your casting of your topping, and then you go up. This system basically repeats itself. And then generally 2 or 3 floors will be propped, and then they will start removing the bracings and the proppings. There is an idea about overall how this precast system works. And this is how it looks at site. So at this site, they've already placed the walls of the next floor. Here they're erecting the walls. You can see here, this is cast in situ topping. The balconies are solid cantilevered panels. You can see the props also here for supporting them. The lifting of the wall panels. So what happens is you have a large number of wall panels in X and Y direction. So these have a large in-plane stiffness, as already discussed in some of the presentations in the morning also. How are these connected? At horizontal joints, we have a grouting, as well as we have these reinforcement bars, which are going from one panel in the other panel. So I'll show that in detail how that actually looks. This is your precast wall. This is a very simplified way of showing it. For some people who don't know how the system works, you have these large dowel bars. Minimum size would be 16 mm, but generally it would be 20 mm or 25 mm dowel bar. Obviously, the wall reinforcement is not shown in this picture. Then the next wall sits on top of that with an oversized tube. It is a steel tube, and then the horizontal joints will be grouted, and all the tubes will be filled with a high-strength grout. So this is generally what kind of connections that we had used in this project. So how does it look in your mold? It's basically a corrugated steel tubes, which are lapping with the reinforcement of the wall. So all these walls, all the structural walls have a double reinforcement. And there's going to be a lot of extra confinement reinforcement around these grout tubes. So again, a little bit of simplification. If you have a column, just one more time to show how the system works. You have your column, you have your slab in between. Then you have a next column, and you have your tubes, and then filling it with grout. So how does it look at the construction site? This is a typical floor, and you have all these, like I said, 20 mm, 25 mm starter bars coming out, on which the wall panels and the structural elements of the next floor are going to come. You're going to need some shim plates to level that, and then the wall panels will be lowered here, and, oh, wrong button. Be lowered here, and then that joint and all will be filled with grout. So we had seen a little bit about connections and all, and how does this system actually work? So what we're having in here is that we have this starter bar, or dowel bar, which is in the center of your structural element, your structural wall, and you have your mesh, which is at the outside, the exterior. So there is a gap, a distance between that, and see what happens in case of compressive force is that everybody will understand the compressive force will transfer to the grout and transfer to the reinforcement. But what will actually happen in case of tension? So the tension will be at the end of the shear walls, because we have a system where overturning moment will generate tension and compression at the ends of the shear walls. So this tension will be inside your wall, and it has to go through this dowel bar into your structure below, either your foundation or your wall below. So what will happen is that through this confinement reinforcement, you will get compressive struts, which will then transfer that tension to this dowel bar. So that is the main concept and the idea behind this. So what is important is that, like I said, you have shear walls, you have your tension and compression at the ends, that the yielding areas, especially in high seismic zones, we need to take care of that. That was already discussed in the previous presentations also. So a general arrangement, if I look at wall elevations, we'll have longer starter bars or connector bars at the ends of the panels, and the middle of the panels will be more utilized to transfer shear. And if we zoom in on this joint, I have here a section where I have a wall panel below, I have my slab in between, and then I have the wall panel above. And we have the starter bar in the center. So we have that confinement reinforcement. We have the edge reinforcement also in the panels. And if you look at the top view of that section, then you will see we have the confinement stirrups with the corner bars everywhere. So to properly assure that we have ductility in these locations. And again, in elevation, it looks something like this. Some of the reinforcement is not shown, so the slab reinforcement and the mesh reinforcement is not shown. But we have a confinement reinforcement here around these grout tubes. At the construction site, it will look like this. You have your wall, and we have these larger dowel bars coming out. We also have these short reinforcement bars coming out. Those will be lapped with the slab reinforcement. So wall panels, these are the openings of the grout tubes. Those will be filled with the grout at site. This is the preparation of the grout mix. Yeah. And the filling of the horizontal joints, filling of the tubes. Now, as an alternative for this system of dowel bars, which are generally, this is the conventional system where we need a full lap length, or actually we sometimes we want to have a little bit of extra lap length. An option which was also shown, I think, by Mr. Sanjeev in the morning is the splice sleeve system, which is basically an iron cast grout tube, an iron cast tube, which is a lot shorter and has been designed like that with a very short anchorage length in its design and tested as well. So this is a tested system. It can transfer that tensile force, and it is as well as a continuation of your reinforcement. So there are two systems generally in the market. There's one with a threaded end, where what they call a factory dowel. That is a dowel which is inside your precast element. And then this is the dowel which comes, what they call a field dowel, which is the dowel which either comes from your cast in situ structure or which comes from your wall panel or column below. The other system, which is very much similar, but in this system we have a longer iron cast tube, in which the factory dowel is not with a threaded end, but it's just fitted in here, and then the whole thing is grouted. So there is an inlet. Generally, there's a grouting inlet and a grouting outlet. So these are grouted with a pressure pump grouting system. So this is an alternative. I mean, it looks like this. So some companies in India are using this also. There are some advantages to this also, as well as maybe some material saving or cost saving. So those were the horizontal joints and the connections. Then the vertical joints, oh, that goes very fast. How did that happen? Hold on a second. I'm going too fast. One second. Here we go. So in the vertical joints of the walls, we have several options, but generally we provide these kind of loop boxes. Even if it's structurally not required, we can have these to ensure also water tightness. So it will just give you a little bit improved performance instead of only providing a unreinforced shear connection, or I mean, you would say a box connection. So you can provide these kind of grooves at the end of your wall panels and just fill them with grout at site. Or you can reinforce them with these loops, which will give you, I mean, structurally not that much, because it's a system which is not approved for seismic forces, but it will give you a better water tightness at your exterior joints. The advantage of this system, when we use it in Europe, where it's specially designed for wind loadings, which are like majorly non-dynamic loads in low-rise structures, it is actually utilized to transfer shear forces. If we really need a strong connection between a monolithic connection, you could say, between walls or columns, you have to make it as a wet joint. So you need to have reinforcement coming out from your precast element, either the end of your walls or your columns, lap it with stirrups, confine that area, place longitudinal bars, and then place a shuttering and concrete it. So then it becomes a continuation of your structure, and it becomes like, so this is something you have to think about in your design. Where do you want to have this? Where do you need this? And how does it look? A little bit like this. You have these walls with reinforcement coming out. Then you have to place all the confinement reinforcement and longitudinal reinforcement. Then you concrete it, and then you go up. So these are precast, the yellow ones, and the gray part is cast in situ. Going now to the slab system. So the slab system, as I said, was a half slab system. So you have your precast wall structure here, and then we fit these room-sized precast slabs on top of this. So this system, what we have, the bottom reinforcement inside the precast slab, and all the top reinforcement will be placed on that lattice girder. And then a lot of additional reinforcements will be placed at the joints and at the side. Generally, this system, the advantage of a lattice girder reinforcement is it's a system which is made by machines. So we love that in Europe, where we don't have to really put in any manual labor. It's a very industrialized process. So for India, that sometimes might be a little bit expensive. So there could be some alternatives to this, but this is how it looks. You have your precast, generally 50, 60 mm thick, roughened at the top also, to create a good bonding with the concrete that you're going to pour on this. And then these lattice girders. So a lattice girder is, it's a lattice girder made with reinforcement bars by a welding machine. Alternative could be a system where you have sort of stirrups, which you make small beams inside your precast slab. So this could be done manually. So this is an option for Indian market. So detailing-wise, if you come to the wall with slab connection, is that we have a precast where we have these lattice girders coming out, and the top reinforcement will be placed here. Here we have these dowel bars which we saw from wall to wall. And what we did in this particular project, we got reinforcement coming out from the top of the wall, which we were bending down, and which we were lapping at the bottom and at the top reinforcement. And we were playing all this tie reinforcement also at all the edges, all around the structure, interior walls and the exterior walls. So slab system as such, what we do at the intermediate supports is that we also continue the top reinforcement. So it's a continuous floor span system. So what we do at the interior supports is slab will be resting from both sides. We will place reinforcement on top of the planks. This is one option. There could be some other options also, but this is what we did in this project. We had the reinforcement from the wall panels lapping with the top reinforcement, and top reinforcement would continue. So as a continuous system, same as a, you could say, cast in situ floor. Oh, sorry. A picture of placing the slabs. So they're room-sized slabs. And then on top of that, you're going to place all your electrical conduits and everything. So this is a propping system. As they're room-sized slabs in this project, they were supported all around. So generally, most of the slabs were supported on 4 sides. As such, for the structural integrity, as also shown in the morning presentations, I mean, it is important to include all that tie reinforcement in your slab. So that is what we like with this system, as it's a very much composite system of precast and cast in situ on top of that. You have quite a good behavior, and you have a lot of, you can say, accessibility for your workers to place that reinforcement at site. So how does it look? it almost looks like a normal, what your laborers will be used to at the construction site. But this is, let's say, your internal wall. You have all this reinforcement coming out, lapping with the top and bottom reinforcement. You have your tie reinforcement also, so that tie reinforcement goes all around the structure. And then you can see here your electricals, which are going back down to the walls. And in this case, the bathroom area was a solid slab. The client wanted to have that, so that is also having reinforcement coming out, which is lapped. And then you pour your concrete, and then it looks like this, with, again, starter bars coming out for the next story. Then the balconies, those were all external solid slabs, and those were made as solid precast concrete slabs. How does that look? This is my half slab before casting the topping. This is the cantilever precast balcony. Obviously, this is supported temporarily. And then we have all our top reinforcement, especially the top reinforcement for the cantilever action, coming out, and it's going to lap in that reinforced topping. So temporary supports, balcony. So how does it look in detail? I have my, let's say, load-bearing wall. I have my half slab, lattice girder, top reinforcement, and then this is the balcony top reinforcement, which goes all the way and gets fully lapped for the cantilever action. We also continue the bottom reinforcement, and we also have some tie bars here, as well as if you're doubtful about your shear transfer here, you can also have diagonal bars crossing this section here, as well as up and down, if you're thinking about up and down kind of reversal of shear force at this section. So this is also something we do a lot in Europe. We actually did that in this project also to ensure. So see, shear transfer through this concrete part might not always be sufficient. So how does it look in the end? My precast balcony and then all this reinforcement coming out, lapping with the mesh of the topping reinforcement. Electricals, your starter bars, and then pouring concrete on that. I think that is how it looks, cantilevered balcony. So this is a picture of a construction site at that time with these apartment blocks. Oh, sorry. And this is how when they were finishing it. A very quick overview of some of the production facilities that they had. So they had a site factory with two bays. One was for the wall panels, the other one was for the slabs and the special items. Including stockyard here, which was extended with gantry cranes from the plant. So this side you had your wall production with battery molds, and then here slab production, balcony production, as well as some other items. The reinforcement cage preparation was in the other end of the factory. Now, a battery mold system, I mean, I don't have too much of time to discuss all this, but obviously there are some of these suppliers in the exhibition hall who can explain you all the details about these systems. This particular client had two battery molds, which is a system where you vertically basically cast your wall panels. That looks something like this. So it's a system that opens and closes, and then you have your casting, your pouring, concrete pouring bucket where you pour the concrete from the top. Quite an advantage for this project was it was a high seismic zone. We had a lot of reinforcement coming out from the top. That this system proved to be pretty good for at least detailing wise. So this is a panel where you have plumbing provisions in that. And then I had some horizontal tables also for horizontal casting of some of the other walls. There were some special walls in this. In this case, there's a wall which has a corbel. There's a corbel there. So you can't make that in the battery mold system. Basically, battery mold system, you generally make only the solid walls. Storage at site, and then the slab production. Slab production were beds of around 60 meters long, stationary beds on which these half slabs were manufactured. Then we had a lifting frame, so that, I mean, obviously these slabs are a little bit fragile, so picking up these with on multiple points to ensure that they don't crack. Balconies were casted upside down. So this is what you're looking at, is the mold for the balcony with a texture finish. So basically, I mean, it's an exterior part of your building. So when it rains, it gets slippery. So this texture was in the mold. There were various samples that the client looked at. And then after casting, this is the reinforcement fitting. This is that reinforcement sticking out for your balcony, which we saw, which was lapping with the topping. This is now upside down, so they have to flip this. And then when it's flipped, it looks something like this. So this is a rough surface. So when it rains, and there's a little bit of slope also to the rainwater pipe. So we provided some slope. So everything was built in this mold system as such. Then the stairs, so in the stairs we had a similar kind of texture for what we call anti-skid or anti-slip kind of surface. So that was project one. I don't have that much time. I'll go quickly through project two, which is a housing project in Bangalore. This was the site plan. There was, I think, around 81 acres, 6,500 apartments. This is a 3D of that project. So the system as such of the superstructure was same, only in this project there were two-level underground basements which we had made completely as precast concrete. So first have a look. In that basement we had basically the tower area and then the outside the tower, the parking area. So the parking area we made with columns and beams, and the retaining walls were all made as precast concrete, 2-story high retaining walls. So the beams were the half beams, and then we had these half slabs again. These were the retaining walls with the exterior also. Every joint was waterproofed. We had made a special detail for that. So some of the items, these items are more or less same as in project one. We had the wall panels, we had for the shaft walls, we had the U and the L walls. The stairs, in this project we had the stairs including the landing as one piece. And then some of the beams. So these were all, everything was, by the way, non-pre-stressed. There's no pre-stressing in these projects. Also, these are short span beams, so pre-stressing was not required as such. The execution of this project, this is a raft foundation. And on top of this raft, you can see all your starter bars, which are for your precast concrete columns and walls. So we had basically parking, this was the parking area underneath the towers. And on top of this, we would have shear walls. Most of the shear walls would be going directly down. This is in Bangalore with a seismic zone 2. So we had a little bit, maybe more flexibility on having a sort of a hybrid system where we did not continue all the shear walls fully down. So the basement, this is basically the tower structure. Columns and beams and shear walls and larger columns also. And again, it's going very fast. And then the building system for the extended, you would say non-tower basement area. We had the exterior, retaining walls, strip footings with starter bars coming out. And then this is the precast retaining wall. This is the outside, and we made a special reinforced overlap connection to increase the water tightness here at this location. As well as the vertical joints in the wall panels, we had the loop boxes with the longitudinal reinforcement in that. So you can see here, this is the retaining wall, this is the non-tower area where the parking is happening, as well as some of the parking bays are underneath the tower itself. We had a cast in situ part here because they wanted to drive through underneath the tower. So that was something which was very difficult to realize that with precast concrete. So we made that as a cast in situ structure. These are the retaining walls. You can see the waterproofing at each vertical joint. Then other aspect was that the frame system in the non-tower area. So the frame system, as you can see here, is basically precast columns and beams, and then it would be connecting here to the tower area. So this was without secondary beams. It was a half slab system, and everything is normally reinforced. There's no pre-stressing in this. So what happened with the connection of the floor slab to the beam is there was very less provision here of providing a core bell. Client also didn't want a core bell. So what we provided here is the reband reinforcement boxes. So reband reinforcement boxes is basically a factory-made reinforcement which is already bent inside the box. You put that in your molds, you pour the concrete, you bring it to site, you can open that box, and now you can place your slab, and then later you can take out this reinforcement and fully lap it with the topping reinforcement of your slab. So this was for us the first time we were using this kind of concept of reband reinforcement boxes. It's being used in cast in situ construction also for high-rise in India, especially when you have a climbing formwork, which already continues, and then your rest of your structure follows after that, where you want to connect your slabs and your other structures towards your core. So there was a company in Mumbai who made this locally. Otherwise, there are lots of companies in Europe and other places of the world who manufacture these boxes. It's just simple. Actually, it's reinforcement bars, and it's a metallic box which is covered. And if you look inside that box, generally the box is 1215 mm, and all these bars are bent, and then you take them out. So you only have to take in your design calculation that double bending of your reinforcement. So there will be a little bit of reduction of strength in your steel. So this would be my retaining wall, which would, instead of, in case of a double height retaining wall, and we didn't have a provision for core bell here, so we had this reband box. Reinforcement would lap with bottom reinforcement of the half slab and top reinforcement. As well as the box, as it's deep, it will also be filled with concrete. It also increases the shear transfer at that kind of joint. So how does it look? This was a single height retaining wall. This is this box. This reinforcement comes out and it all laps. These are the lattice girders of that half slab system. Half slab system with the propping, the beam, and the columns of the parking area. So here you can see these are the reband boxes, and they're at this side as well. So for the columns, in this case, these columns, we utilized the grout tubes, the grout sleeve, you could say. So we had a very short anchor length in this case. So these were these iron cast tubes, which I showed earlier. So they have a very short anchorage length. I think these are 20 mm bars, and the lap length would only be 200 mm, or maybe even less than that. So this is the cage for the columns, and then this is how your inlet and your grout inlet and your grout outlet, on which you pressurize with a pressure pump, you fill it with grout. So that junction comes together here with your beams, your half beam, and you'll have your top reinforcement running through, so it will be continuous. So basically your top moment as a continuous beam system will be taken care of here. So how does it look in detail? You place your column, you place your beam with bottom reinforcement coming out. So this detailing here you have to work out a little bit when you start preparing your detail drawings. And then your top reinforcement is laid at site, and then you pour concrete, and then your next column will come. Grouting. So this is what they do at site. So there is still some site activity involved, of course, in this kind of system. We found still that especially for residential projects where you have small spans of 4 or 5 meters, that this half slab system is still one of the most flexible systems for residential projects. So here is an overview. These are the towers, and this was the parking area, non-tower area, and then this is our tower here. And then construction. So the superstructure construction was similar to the other project. There was one feature that we had in this project where the sunshades were integrated in the mold. So we had special molds for all the exterior wall panels. So these were not made in any kind of circulation plant or something. These were stationary molds where the sunshade was downwards in the mold. This was the factory that this client had put up. So there were 3 bays. These 2 bays were for a circulation system. So this is a different system where your pallets are moving from one station to the other station. Rebarring, and then they had a plotter for plotting the contours of each precast element. Shuttering, concreting station, of course, and then this is how a finished wall panel would look. Half slabs were also made in the circulation plant. So this client had invested in this lattice girder welding machine. So like I said, that is a machine where you feed here on a roll, you feed the reinforcement, and that is an industrialized process where here at the back the lattice girders will come out. The special molds, so these were all special molds for beams, columns, beams, columns, staircases. Last project, I will spend 5 minutes on this one. So this is precast villas in Greater Noida. It was a long time ago that we did. This is a 3D visualization. So some of these villas were made in precast concrete system. We had a lower ground, basically a basement, underground basement. Then we had a ground floor and first floor and second floor. Now the design approach, basically again it's same, it's wall panels. It's just a low-rise structure, but wall panels as such. The only difference in this project was the slab system. So the slab system in this project was hollow core as a pre-stressed. Not really required because the spans were not so much, but the client had invested in a hollow core plant and they wanted to utilize this system. So we had to put that. Load-bearing walls were 150 mm and the precast slabs were 150 mm pre-stressed. This is an image of the hollow cores, 150 mm thick. The walls, some of the balconies, the stairs, landings. Execution, we had the basement, so only the strip footings were cast in situ, then on top of that we put the basement walls, and then precast structure, mainly wall panels. And then this is a little bit the difference with all the other projects, the hollow core floor slabs. So as you can already see, we had a lot of openings here at the end of these slabs. I will show you why we did that. The thing was actually that, see, the thing is with hollow core, you don't need any propping system as such, and that is a major difference with the half slab system. But you still need to provide a topping on this for the structural, integrity, the diaphragm action, and we also have to connect all these slabs to your load-bearing structure, to your beams, to your walls as such. So the advantage here you can see, lifting of hollow core, very simple. You just place it on your whatever beams or something, no propping required. But then here at the ends, it's more complicated, I would say, compared to the half slab system, because we still want to have a proper connection here. And there are some, IS codes which are saying, 50% of your bottom reinforcement or something has to lap at the support. So to follow that, these are pre-stressed slabs, so I cannot take out a pre-stressed reinforcement or such. So we had provided these pocket openings, and in that we would place extra reinforcement. So it would be something like this. This is my load-bearing wall. We already had, because we had very much squeezed thickness, only 150 mm thickness of wall panel. So there was barely any kind of bearing length left here. So in these pockets, we would place these, you could say, very long stirrups, which would actually sort of extend the bearing of the hollow core floor slab on the wall. So it would be fully resting on the wall. We had some tie reinforcement here, as well as we had reinforcement coming out from the wall, which we would bend down at site and which would lap with the topping reinforcement. All in all, for a villa, it was a bit complicated, I have to say. But I would say for large-scale housing, and where you have a little bit larger spans it's a good system, and obviously we have seen many projects in India already where we have commercial buildings with 10, 11 meter spans where this holocaust floor slab system is ideal system as such. So this is a few more overviews of these connections this is an interior support, some tie reinforcement. Yeah, it's not really complete, but there would be some tie reinforcement also placed here. And then concrete you would pour over this. So this is the ceiling you get. So disadvantage of this system a little bit is you get the joints in the ceiling. Some people don't like that. Balconies were cast in situ here, but were supported, I think. They were not cantilever. Precast staircase, and this is how it looked in the end. And then the factory they had two plants, one for wall panels, one for hollow core. So hollow core is a system where you have long line beds where you do pre-stressing. And you have this extruder or slip former, which basically makes your hollow slab. Looks like this. And then the wall panel plant, this particular client had a plant where each and every mold could be picked up by a central shifter unit and would bring it from one workstation to the other workstation. So all these pallets, which are generally 4 meter by 12 meter, I guess, could be picked up by this machine here, which we call a central shifter, and bring it from one workstation to the other workstation. Every workstation, you have specialized workers who do one activity, and this thing will bring it to your station. So you have rebarring, you have the fitting of the conduits and all that stuff, shuttering, which has to be put. So shuttering generally will be put by the magnets on these pallets. The central shifter, so this will be moving up and down all day long. It's operated by the control room, and then it can just pick out. So here you have multi-level curing rack, you would say. It can be covered also, where you can do a steam curing as well. Concreting, yeah, this is the curing rack. So at the end of the day, this is how it will look. Thank you. That's it.
Thank you, Mr. Bob. Your presentation is excellent. Actually, you have given detailed drawings and then detailed photos so that everybody can appreciate. Yeah. Yes, even laymen also can understand. So, yes. I request, okay, Samir Patel Saab, Ashmir Patel.